Okay, guys, in this next section, we've got a lot going on here. So I'm going to be breaking this one up into a whole bunch of shorter videos. And in this first video on classifying chemical reactions, I'm going to talk about electrolyte solutions, and I'm also going to discuss solubility rules. Okay, so this learning objective right down here. So let's get into it. On this slide, I'm talking about solutions of ionic compounds, where you have ions that are mobile within the aqueous solution. So we're going to distinguish between two types of solutes. The first type, the non-electrolyte, this is a substance that when it dissolves, it does not form ions. Okay, and so the term electrolyte means electricity loving, and so a non-electrolyte is a solute that does not conduct electricity in solution. Examples of that would be some different types of sugars, for example, glucose, or alcohols like methanol and ethanol. These are substances that dissolve readily in water, but they do not produce ions, and so they are considered to be non-electrolytes. Electrolytes, however, do produce ions in solution, and these ions are capable of transmitting electric charge as they move through the solution. So electrolyte solutions conduct electricity. Now, electrolytes, the solute, can either be an ionic compound or it can be a molecular compound. The ionic compounds are fairly straightforward. So, for example, sodium chloride consists of sodium cations and chloride anions. When you dissolve that in water, you form these ions, right? The ions are already present in the solid solute, and they simply dissociate from one another when you dissolve the salt in the solution. However, molecular compounds like hydrogen chloride can also dissolve to form ions, typically through a reaction with water. In this case, the hydrogen chloride will form protons and chloride anions. However, in HCl, we don't have protons and chlorides bonded together in an ionic compound. This is a molecular compound. So molecular compounds can also form ions. So molecular compounds can also be electrolytes. It just depends. Ammonia is another example of a molecular compound that when it reacts with water, it forms ions in solution. It forms the ammonium cation and the hydroxide anion. So what actually happens is the ammonia grabs a proton from the water, that gives us the ammonium, and then what's left behind when you take a proton from the water is this hydroxide anion. You may notice that I have used one-directional arrows for these first two reactions, and I've used a bidirectional arrow for this third reaction. And that actually indicates something about these electrolytes. Strong electrolytes are ones that completely dissociate in aqueous solution, so we use a one-directional arrow. Weak electrolytes, however, only partially dissociate, and so ammonia is an example of a weak electrolyte. So this reaction occurs to some extent in the forward direction, but it doesn't go 100% to the ions. There's a significant amount of back reaction, and so we use the double-sided arrow. Okay, so we use one-directional arrows for the dissolution of strong electrolytes, and we use these bidirectional arrows for the dissolution of weak electrolytes. In this slide, what I'm introducing are the solubility rules for ionic compounds. So not all ionic compounds will dissolve in water. Some ionic compounds are classified as insoluble, others are classified as soluble, and some are classified as slightly soluble. We are simply going to classify ionic compounds as either being soluble or insoluble. And these are the rules that we need to know and be able to apply in order to determine whether a given ionic compound is soluble or insoluble. So here are the rules. So if an ionic compound contains a group 1 cation, so this would be something like lithium, sodium, potassium. Let me pull up the periodic table. If your ionic compound contains any of these group 1 cations, then that compound is soluble in water. So you'd classify it as soluble. Alternatively, if it contains the ammonium cation, then it's also completely soluble. Okay, so that's rule number 1. Rule number 2 concerns anions that are very soluble. So nitrates, acetates, chlorates, these are all very soluble in water, regardless of what the cation is. So if you see a nitrate or if you see an acetate in the ionic compound's formula, then you are to regard that as being soluble. Halides, so ionic compounds that contain fluoride, chloride, bromide, and iodide. These are usually soluble, although there are several exceptions. The exceptions are silver, mercury, and lead. Okay, so if you had, for example, silver chloride, it would not be considered to be soluble because it is an exception to this rule. So some of these solubility rules, they have exceptions. I have a very dumb way to help you remember these 3 exceptions. I call these the poison metals, right? We know that lead is poisonous. Mercury is also poisonous. And for all of you Twilight fans out there, silver is poisonous to werewolves. Okay, so I call these the poison metals to help you remember that. Lead, mercury, and silver for werewolves, at least. Sulfates. So if a compound contains SO4, it's soluble. There are some exceptions. There's our 3 poison metals, and then there's also strontium and barium, which you'll find here at the bottom of the periodic table. You might even add in calcium as well. Okay, so sulfates are generally soluble, except for our poison metals and these lower group 2 cations. Let's see. Here we're flipping over from things that are soluble to things that are insoluble. So if you see a carbonate or a phosphate or a sulfide, these are generally insoluble except when paired with a group 1 cation or ammonium, right? Rule number 1 trumps rule number 5. Okay, so sodium carbonate is very soluble. However, magnesium carbonate is not soluble. Hydroxides are generally insoluble, except, of course, for group 1. Okay, so lithium hydroxide, sodium hydroxide, potassium hydroxide, these are all very soluble. Likewise, calcium, strontium, and barium hydroxide are also soluble. Okay, so the rule for hydroxides is that hydroxides are generally insoluble, except for, where'd my periodic? Looks like I accidentally closed my periodic table. Get it back. Hydroxides are generally insoluble, except for group 1 and calcium, strontium, and barium. All other hydroxides you would regard as being insoluble. Okay, so these are the rules, and we need to learn how to apply them. So I've got some conceptual questions here. In this first part, which of the following species would you expect to be a strong electrolyte when placed in water? Okay, so is the compound soluble or insoluble? Is it an electrolyte or a non-electrolyte? Okay, so for ammonium chloride, right, it contains the ammonium cation. And the rule number 1 is that ammonium containing compounds are very soluble. So NH4Cl is a strong electrolyte because it's very soluble. Magnesium bromide. It contains a halide. Halides are generally soluble except for our poison metals, lead, mercury, and silver. Magnesium is none of those, so magnesium bromide is also a strong electrolyte. Water. Water is not an electrolyte. Okay, so water, not an electrolyte. HCl. We've already talked about that one. That's an acid. In fact, it's a strong acid, and so it is a strong electrolyte. It's going to form H plus cations and chloride anions. Calcium phosphate. That's essentially what your bones are made out of, more or less. And bones don't dissolve in water. And so calcium phosphate, it's a phosphate. Phosphates are insoluble, is not a strong electrolyte. We would classify it as insoluble. CH3OH. This is an alcohol. It's not a hydroxide, and that brings me to this point here. So I wanted to point out the difference between hydroxides and alcohols. Hydroxides contain a metal and the OH group. We might also have calcium OH2. These are hydroxides. You have a metal cation and the OH anion. Here, there's no metal. It's all nonmetals: carbon, hydrogen, oxygen, and hydrogen. So this is not a hydroxide. This is an organic compound, and the OH group makes it an alcohol. It looks like the structural formula for this looks like this one. You have the CH3 group, and then the oxygen, and then the OH group. So as we'll learn, these are covalent bonds that I'm representing by these dashes, where electrons are shared, whereas in sodium hydroxide you have electrostatic interactions between a cation and an anion that keep the ions in the crystal. Okay, so there's an important distinction between hydroxides and alcohols. Look for the metal. If you see the metal paired up with OH, it's a hydroxide. If you see a bunch of carbon and hydrogen, it's not a hydroxide, it's probably an alcohol. When methanol dissolves, it does not dissociate into ions, so methanol is a non-electrolyte. Okay, we have some follow-up true or false questions, and so we'll just evaluate each one. Ionic compounds always produce a significant number of ions in aqueous solution. It sounds good, but this is not true because certain ionic compounds are not soluble. Therefore, they do not produce ions in solution. A great example of that is the calcium phosphate. It's an ionic compound, but it doesn't dissolve in water. So A is false. A molecular compound can be either an electrolyte or a non-electrolyte. That statement is true. Hydrogen chloride is a strong electrolyte. It's a molecular compound and it's a strong electrolyte. Methanol is also a molecular compound, but it's a non-electrolyte. It doesn't form ions in solution. So B is true. Statement C. Soluble ionic compounds are strong electrolytes. That's typically the case. So C is more or less true. You'll talk about that more in the second half of general chemistry, where you'll study solubility in a lot more detail. Water conducts electricity, so whenever water is present, we should expect a strong electrolyte. That's essentially true. It's partially true. Water does not itself conduct electricity, so pure water is really a non-conductor. However, all natural sources of water contain electrolytes, and it's the electrolytes within the water that conduct electricity. So the statement is a little ambiguous. Ultimately, it's true. Samples of water conduct electricity, so there are strong electrolytes in them. That part's true. However, if you had pure water, it would not conduct electricity. Statement E. Some molecular substances completely ionize in aqueous solution. That's true. HCl is a great example of that. And there are other strong acids as well that we'll look at in forthcoming videos. All right, here we are going to practice the solubility rules a little bit more. And I'll point out that this is not enough practice when we get through all of these. You want to use the end of chapter questions in the textbook to practice these solubility rules in more detail. And I can't overstate the importance of solubility rules, especially if you're going to be continuing on to the second half of general chemistry. They are used all over the place in that course, and so you really do need to know them going into the next chemistry course. So you should practice them. So we want to evaluate whether these compounds are soluble or insoluble, and try to understand why. So for this mercury, let's see, this would be the mercury 2, no, this would be mercury 1 chloride is the name of the compound. The rule for halides is that they are generally soluble except when paired up with the poison metals. And mercury is one of our poison metals. And so we would classify this as insoluble. For part B, potassium iodide, okay, we've got a halide, and then we've also got a group 1 cation. Anytime you see a group 1 cation, you know that it's soluble. Part C, lead 2 acetate. I'll go ahead and write the formula. Two of them. Acetates are always soluble. It doesn't matter that it's got lead. So this is soluble. Part D, sodium bromide. We've got a halide. Halides are usually soluble, especially with paired up with a group 1 cation like sodium. So this guy is soluble. Part E, barium hydroxide. Hydroxides are usually insoluble, but there's some exceptions. The exceptions are your group 1 cations, and then the cations here at the bottom, barium, strontium, and calcium hydroxides are soluble. So barium hydroxide is soluble. Part F, calcium carbonate, which is limestone. It's also what chalk is made out of, and essentially seashells as well. Seashells don't dissolve in water. Carbonates are insoluble. Now, calcium carbonate does dissolve in water, as you know if you live around here in cave country with our hard water. However, generally speaking, calcium carbonate is not very soluble. So we would consider that to be an insoluble substance. Like I said, you want to practice these, use the end of chapter questions from the textbook to make sure that you can get all of these different rules down. And so with that, I'm going to end this video, and we'll pick up with molecular and net ionic equations in the next one.